Swayam Prabha. Digital India. Educated India.
Welcome back to the course of mechanics of solids. So, in the last lecture we were talking about the stability and instability of a slender member, right, and the buckling load. We calculated the critical load of the buckling load, that was equal to twice KL, that critical load, right. And there we saw that if your load is below your critical load, then there is no problem, system will be under stable situation or the stable condition. But once your load, applied load on a slender member crosses your critical load, then basically you will be entering the unstable zone, right, and that might create the problems. Then basically the whole column will be buckle or sway, and different kinds of, I mean, say unstable situation, or the instability will be coming to the system. Okay. So, now in the last lecture, if you recall, we considered the load. Okay, we calculated the critical load based on the load was concentric, that means load is acting, that load P is acting along the center of the, along the center line of the, or the along the axis of the slender member. But now this might also can happen, right, if you have the load which is acting on the structure which is little bit off centered, right, that means you are having some small amount of eccentricity. Okay, a small amount of eccentricity you are having, okay, say that is nothing but epsilon you are saying. Okay, so if you have the system which is carrying some eccentric load, then what will be the magnitude of your critical load? Okay, so let's find out that. Let's do the same thing by equating the restoring torque and the upsetting torque. We will be getting that. So, if you look at this problem, this is your free body diagram. Okay, this is your free body diagram. So, this force will be coming from the right hand side spring, and this force will be coming from the left hand side spring, because right hand side spring will be experiencing the compression and the left hand side spring will be experiencing the tension, and this is the force P. So, now instead of x, your distance from the axis, that is the line of action of the force P, okay, the distance between the line of action of force P from the axis will be x plus epsilon, that is your eccentricity. Okay. So, we can simply write P into x plus epsilon. Okay. What is that? That is your upsetting torque with respect to point B, that means at the support, okay, is equal to twice K into XL, that is your restoring torque. Okay. From this I can write down x equal to epsilon P by twice KL minus P. Okay. So, this is the distance. Okay, what is this x? X is the distance, maximum distance, which will, up to which there is no problem. So, system is under equilibrium, or system is under stable situation. Once you cross this x, then immediately system will be under unstable situation. So, now if you look at this figure, if you draw the P versus x, x means that distance. Okay. So, what is happening here, for small values of P, okay, for small values of P, your x is also very small. That means when the load is quite below your critical load, then the system, that your vertical member will not be experiencing this much of lateral movement or the lateral sway. Okay. Once your magnitude of P is reaching near to the P critical, then your x is quite large, that you can see from here, right. So, once it is reaching the P critical value, okay, immediately your x is becoming very, very large. That means, so that as an engineer your aim will be always to avoid to reach up to the P critical. So, if you want to avoid P critical, then you should know what is the value of P critical for a particular member, particular vertical member, or the like column, or like your shaft, whatever. So, you should know what is the magnitude of your P critical. Okay. So, let us find out that thing now. So, now we will be talking about elastic stability of flexible columns. Okay. So, now let us look at this figure. So, we are just considering one member here. If you look at in xy plane, okay, we are considering one slender member, like I mean right now we are considering the horizontal member, and there is no problem if you consider the horizontal or vertical, I mean, both are same, right. If you consider the same loading system, whether you consider horizontal or vertical, that does not matter. Okay, anyway, so this is some horizontal member we are considering under the load P, compressive load P, and as I told you that we are in this particular chapter, which is very unlike to the other chapters, previous chapters. In this particular chapter we will be considering the equilibrium, or we will be considering the equilibrium condition, okay, at the deformed or the unstable or the say displaced situation, okay, as I told you. Okay. So, now this is the force which is acting on this member, and this member is carrying some say distributed load Q over the whole length, and this V is your departure, that means the displacement, okay, along the y direction. This is the V. So, this I mean you can find out. So, as you are putting the load or as you are increasing the load, this V will be increasing because of the instability happening. So, now we are considering one small element, okay, we are just considering one small element, and that element is blown off here, okay. So, this length of the element say dx, and that is here, okay. So, now you have load P which is acting like that, okay. For every cross section you will be getting the compressive load P, and this the line of action of this side, this is your say, if you say this is your positive phase and this is your negative x phase. So, on the positive x phase, whatever line of action of P you are getting, the negative x phase you will be getting different line of action, right, and the distance between these two lines of action is say dV, okay. That is the difference between these two lines of action, because now the system is getting buckled, right, that the system is getting say some or experiencing some lateral movement, okay. Now, as before, so we are considering the column or like the slender member. So, we will be having MB on this face, V, that is the shear force. On this face you will be getting MB plus DMB, some increment, and on this face you will be getting shear force V plus dV, that is some increment. And this is the say I mean quite a good approximation, that Q into dx, that is the concentrated force, okay, line load, okay, which is acting at the center of the member, okay. So, that is coming because Q into dx is nothing but the vertical concentrated force acting on that particular member instead of considering the distributed load, okay. So, once we are considering this free body diagram, then what we can write for the element to be in equilibrium, for the element to be in equilibrium, what I can write, if you look at this figure, V plus dV So, we are now just considering the force equilibrium, that means summation of all the forces along y direction is 0. Okay. So, V plus dV minus V plus Q dx equal to 0. Okay. Now, if I consider the moment equilibrium, then I can write this is coming from summation of Fy equal to 0. Similarly, if we consider the moment equilibrium, mb plus dmb, okay, minus mb plus v into dx by 2. Okay. So, we are considering the moment with respect to the center of that particular element, small element, okay, plus v plus dv into dx by 2 plus p into d small v. So, dv is the, as I told you, that is the distance between the lines of action of p on positive express and negative express. So, that must be 0. Now, we are considering, or we are neglecting the higher order term like dv dx and all those things. We are neglecting that thing, and we can simply write from this, we can write dv dx equal plus q equal to 0, okay, and from this I can write d mb dx plus v plus p into d small v dx equal to 0. So, this say equation 1. Okay, fine. I hope there is no problem. Okay. So, now just we are neglecting the higher order term. So, now we know, already we know from our previous discussion that EI d2v dx2 equal to mb, right, already we have derived that. Now, we will be putting that relation here, okay, in the second equation. So, that can be written as d dx of mb. So, instead of mb I can write EI d2v dx2, okay, plus v plus p into dv dx equal to 0. Okay. Or further we can write. So, now what we are doing, we are taking derivative with respect to x on both sides. Okay. So, therefore, I can write d2 dx2 EI d2v dx2 plus dv dx plus p d2v dx2. I can write by taking the derivative on both sides, okay, with respect to x, of course. Then this can be further written as EI d4v dx4, okay, plus p d2v dx2 is equal to minus dv dx. Okay, fine. Now, what is minus dv dx? If you come to this equation, minus dv dx is nothing but q. So, that can be written as equal to q. Now, as we were talking about the column, though we considered that as the horizontal member, but column generally is a vertical member, right, and quite often, I mean most of the times, the column is carrying the vertical load, no lateral load, right. It is very unlikely the column is experiencing the lateral load. So, if it is not experiencing the lateral load, then we can say or we can consider Q equal to 0. Q is nothing but the lateral load. So, if you consider that this horizontal member, so we consider this as a horizontal member, but this is a kind of column, right? Only it is carrying the, if you invert that thing, so that will be like this. This is P and lateral load, and it is very unlikely that it is carrying the lateral load, right, the column. So, therefore, we can neglect that, or we can say Q equal to 0. So, when your EI and P both are constants, because EI is constant, that is why I could take EI out. Similarly, P is constant, therefore, I could take P out. Okay. So, they are constants, and there is no transverse load, that is Q equal to 0. Okay. Then we can write EI d4 V dx4 plus P into d2 V dx2 equal to 0. So, that was equation say 2 I called, and this is your equation 3. Very, very important equation in buckling. Okay, fine. So, EI d4 V dx4 plus P, that is a vertically applied, or I mean if you consider a column, that is a vertically applied force, into d2 V dx2, where V is nothing but the lateral movement or the lateral deflection. Okay, fine. In case of column, there is a lateral deflection, but as I showed in the problem, we started with the problem because you know the beam bending. So, that is why I showed like that in the horizontal member, and then we solved that. But actually we are solving the column problem, but no matter whatever structure, whether it is vertical or say horizontal, that does not matter. Okay, that does not really matter as long as you are your forces and your moments and all those things are calculated properly. Okay. Now, if you look at, I mean I am not going to solve that equation. So, this is your fourth order differential equation, and if you want to solve this equation, that equation basically the solution of equation you can consult any mathematics book, you will get that the solution of equation 3 will be V equal to C1 some constant, C2x, C3 sine root over P by EI into x plus C4 cos root over P by EI into x. So, equation say 4. So, that is the solution of this differential equation. It is nothing to do with the mathematics, I mean mechanics, this is purely coming from your mathematics. Okay. Now, what we are considering? We are considering, basically we are considering now how you will get these constants? By putting proper boundary conditions, right. Now, we are considering one column which is fixed at the bottom, which is carrying a load P, and due to that load P it is showing the instability. Okay. Let us say, so this kind of system we are considering. Now, this is a column which is free at this end, at the top end, and fixed at the bottom end. Now, this is equivalent to, I mean this is same actually, we are talking about the horizontal member, right. So, it is basically equivalent to something like this. You have one beam, okay. So, this is your x direction, this is your say y direction, this is the beam, okay, and you are applying a load P, and because of that the beam is getting bent like that. Okay. So, both are same, only the orientation is different. It is the vertical, it is the horizontal. So, because we are quite familiar to analyze this kind of horizontal member, because we have seen the beam bending and all. So, therefore, we are considering like this, but however, this V here it is along the y axis, here it is, if you consider this is your y axis. So, you can say that V is same. So, both the things are same. So, whether we consider column, vertical member or horizontal member, the analysis process or the steps involved are same. Okay. So, now if you consider this system, okay, now at what are the boundary conditions you can think of this kind of problem. At x equal to 0, at x equal to 0 means at the fixed end. What are the boundary conditions for fixed end? There is no displacement, no rotation, right. So, I can simply write that gives me V equal to 0 and dV dx equal to 0. Agreed. Now, because I need 4 boundary conditions for getting 4 unknown constants, right. So, 2 boundary conditions we have got. Now, one more, at x equal to L, what is happening? At x equal to L, what I can write? Your bending moment is 0 as well as your shear force is 0. Agreed? At the free end, that means at the free end your bending moment is 0 as you know, and your shear force must be 0. Agreed? So, these are 4 boundary conditions, and now we will be using these boundary conditions to get our unknown constants. Okay. So, now already we have seen at x equal to L, okay, your EI d2v dx2 is equal to mb is equal to 0, okay, and your shear force is also 0. So, EI d3v dx3, that is the shear force, okay, plus P dV dx is equal to minus V, which is 0. So, this is equation say 5. Already we have derived that, okay. So, if your V is 0, then at x equal to L, these equations must be satisfied. Okay. Now, putting these boundary conditions in equation 4 and 5, putting these boundary conditions, this is your equation 4 and this is your equation 5, what we will get by putting this, putting the boundary conditions in equation 4 and 5, what we will get? C1 plus C4 equal to 0. Say this, let us say this is equal to equation 1. Then C2 plus C3 root over P by EI equal to 0. Say this is equation 2, and minus C3 P by EI sin root over P by EI L minus C4 P by EI cos root over P by EI into L equal to 0. So, this is equation 3, and the last equation is C2P equal to 0. This is equation 4. Okay. Now, if you look at these 4 equations, the right hand side of these 4 equations is 0. Okay. right hand side of each and every equation, all the 4 equations is 0. Then what we can say? We can say that C1, C2, C3, C4 all are 0, right. That could be another one solution actually. C1, C2, C3, C4 all are 0. Read it or not? That is one of the solution, that is the obvious solution, right. By saying this set of simultaneous equations. But if you put C1, C2, C3, C4 all at 0, then what you are getting? Basically you are getting that P, okay, this is actually saying you the true equilibrium solution, and it says that the beam or rather column does not bend at all. That means V is 0 completely, small v is 0. So, there is no bend or no lateral movement, okay. But it is the trivial solution, that is the stable situation, that we do not want to explore right now because we know that, okay, that is your stable situation and that is the trivial condition. But that means you are applying the load and that load is not creating any kind of lateral movement of the column, okay, or the beam as I showed you, whatever, right. But we are not interested in that kind of solution. This solution will give you the trivial solution. That trivial solution, I mean, already we have taught and we have analyzed, I mean, so many times about that kind of situation when the system is stable. Now, actually in this particular chapter, we are looking at the unstable situation, right. So, therefore, we are looking for a non-trivial solution where all the constants, I mean, some of them may be 0, but all the constants cannot be 0. Then only you will be getting some amount of V, the small v, that is the lateral displacement, okay. So, we should look for the non-trivial solution to explore the instability, okay. So, we will do that thing in the next class. So, I will stop here today. Thank you very much.